My talk today is on toxicology in the veterinary area, but from the laboratory perspective. Okay, what I will cover. Firstly, just an overview of the DDLS laboratory at DPIRD, the sort of testing technologies that we use for tox, the strengths and weaknesses in our testing, some of the approaches that we've taken in the past to tox investigations, and what's in the pipeline for tox testing in the future, some advice on collecting and submitting samples, and a list of resources. And just a reminder that I'm not a toxicologist, my area is in the measurement of toxins. A quick overview of the DDLS Biochem Lab at DPIRD. DDLS stands for DPIRD Diagnostic Lab Services. We have routine services that would be found in any clinical lab, such as clinical chemistry with diagnostic panels. We also cover vitamins, we cover minerals, and we cover toxicology. Monofluoroacetate. We do a toxin screen using an instrument called a GC mass spec. We do acetylcholinesterase as an indicator of OP pesticides. We do lead, blue-green algae ID is done, cardiac glycosides, cyanide, nitrates, and botulism. Our lab has also done a lot of support for research projects using a wide range of specialized assays that we've developed, for example, amino acids, fatty acids, etc. The reason why I mention this is that it means that we have the capacity to expand our services and try different approaches in the area of toxicology. We've got the means for method development, in other words. Our focus is in the area of toxicology is basically to increase our tox services over the coming years, but always with an emphasis on those toxins that can or may have a potential to impact on food safety. This is a requirement under our DPIRD biosecurity management. The main technology we use in our lab for measuring toxins, or the most powerful method, is chromatography. Simply, we just do an extraction of the sample. We then place that extract into the instrument, the chromatography instrument, and that separates out all the compounds within that sample, and by separating them out allows us to detect or quantify the toxin. Another approach is that's widely used elsewhere but not in our lab is methods based on antibodies, and I've just given a bit of information on that on the slide. The best detector that's available, not only in our lab but in all tox labs, is called the mass spectrometer detector. As we saw, the chromatography instrument separates out the toxins from the other compounds, and these go into the detector. With a mass spec detector, it produces a fingerprint of the toxin by busting up the toxin molecule into fragments using a high energy electron beam. Now, those fragments can be used for quantifying the amount of toxin in the sample, or they can be used for identifying the compound. So we have a commercial database of tens of thousands of chemicals, and the computer system matches the fingerprint we produce against fingerprints within the database to identify the toxin. I'd like to now talk about strengths and weaknesses in tox testing in veterinary field area. I've just taken 4 examples where the tox testing we do has proved useful to the veterinary pathologist. First one was a case which involved sheep ingesting fungicide treated grain. We found the fungicide within the rumen and liver samples from the sheep, and then we tested grain and confirmed that was the source of the fungicide. The second case was a number of bird deaths. This is not uncommon, where we test for acetylcholinesterase, and we find indication through the inhibition of this enzyme that a OP pesticide might be involved. We then use the mass spec detector to search for pesticides in crop contents, and we find a banned pesticide. The next example was sheep that had suspected poisoning from lupin alkaloids. We tested the rumen sample initially, and we found the set of alkaloids, and so we supported the diagnosis. Another one that's interesting because it's not a toxin that's actually directly ingested by the sheep. In this case, it's a toxin that's produced by the conversion of tryptophan, an amino acid, in the rumen to a toxin, 3-methylindole, which causes respiratory disease or fog fever. So the message is that MSD is useful for complex man-made chemicals such as pesticides, etc. And in some cases, natural chemicals that are simple in structure or relevant to food safety in the human field. Continuing on our strengths and weaknesses, we now move to the frustrating situations. Once again, looking at some real life examples. A vet takes rumen and liver samples from dead sheep that have grazed into bushland. They have liver damage and he suspects a plant toxin. We test the samples using MSD, and there are no unusual findings. The vet pathologist in our second example asked the lab if we can test for a specific toxin that he suspects that might be involved in a poisoning case. In this case, iforestine, and he's seen cases of liver damage, and he suspects that the animals may have had exposure to the toxic plant. I checked the database, and the chemical's not there in the database, so we can't detect it as an unknown. I read the literature and tell the vet and senior pathologist that I could set up a screening assay. However, I would need to buy in the pure iforestine standard, and that it would take several weeks to set up the method, i.e. it's expensive exercise. They most often tell me to forget it. So in the first case, we didn't pick up the plant toxins because it's very likely that the plant toxins are not actually residing in the database. The message: we cannot rely on the MSD assay and database to reliably pick up plant toxins. The best solution is to get an assay going for that toxin by, for example, buying in the pure standard and spending the time setting up the extraction and modified extraction if required. And that overall process is expensive. But we have done it in the past. An example is monofluoroacetate, which is a very common toxin in the southwest. And for that reason, we made the investment and got a routine assay. Other approaches that we've taken in tox investigation, the first two are based on bioassays. Firstly, using brine shrimp to test or screen for the toxicity of extracts from plants. This is a well-documented method in the literature. The second method used red blood cells to screen for phototoxins in extracts from plants. We can get indirect evidence of a toxin by measuring changes within the animal. For example, elevated blood citrate levels with monofluoroacetate poisoning, or decreased calcium with oxalate poisoning. We can look for biochemical lesions, for example, the inhibition of the enzyme ALAD caused by lead. We can look for or use clinical chemistry to look for damage to organs. For example, gamma GT used for liver damage in animals exposed to PAs. We can use immunological assays. For example, we extract cardiac glycosides from animal samples or plant samples and then add that extract to plasma and send the sample off to a commercial lab for digoxin testing. And the last approach is one that we've recently experimented with. If we can't detect the toxin directly, then perhaps we can use other chemicals that are characteristic of a toxic plant. In this case, we took lantana. We took extracts from several different sites and found a group of chemicals that were consistent and that would not be normally found in a rumen sample. To test the method, we then mixed lantana with rumen contents and used our MSD screen to see if we could identify lantana within the sample, which we could. What's in the pipeline? We've made good progress in setting up a laboratory for testing biotoxins from shellfish. These are algal toxins that accumulate in shellfish with the aim of providing a service to the WA shellfish industry. We're setting up microcystin LR. This is a toxin found in blue-green algae. We're setting up a new extraction and database to cover veterinary chemicals not currently covered within our MSD screening method. We will be assessing a benchtop instrument for testing ergot alkaloids. It's used for feed samples, but we're going to see if we can adapt it to measure ergot in rumen or tissue samples. Our priority is always to test for toxins that may in future or do have an impact on food safety. We have recently purchased a high-end triple quadrupole mass spec detector, which is very sensitive and has greater scope for increasing the range of toxins we measure. So we're always open to suggestions about toxins that we could develop methods for. Collecting and submitting samples. The liver is always good, being such a vascular organ. A lot of ingested toxins end up there, whether they're lipophilic or fat-loving or hydrophilic water-loving. However, the liver is very good at metabolizing and detoxifying, So sometimes chemicals will disappear very quickly from the liver. However, toxins do vary greatly in their rates of metabolism, so the liver should always be collected. Rumen, gut or crop contents is always a good sample. And any suspicious plants for ID and or tox testing. So I've put in the amounts or suggested amounts for sampling, and clean plastic bags are okay to use. Obviously keep cool in the field and store in the fridge if submitting in the next day or so, but freeze otherwise and ship with cool bricks. We can help you source lab tests from our own lab and also available from other labs within Australia. We also have a number of toxicology reference books, both on fundamentals of toxicology and also on plant toxins Australia-wide. Thanks for your attention.